Our speaker today is Joseph Fehribach, and he'll be speaking on families of Kirchhoff graphs. The floor is yours, Joseph. Thank you.
Thank you. I hope everybody can hear me okay. I'm happy for you to interrupt me during my talk. If you have any questions, I'll answer as best I can. I'm pleased to be giving the seminar today. I want to start off by mentioning my collaborators. I have a number of them. The main ones, at least in the last few years, have been three students, Jessica Wang, Marcel Gietzmann, and Tyler Reese. Tyler was a PhD student who finished several years ago. Marcel also finished several years ago. Jessica finished just last year. Marcel and Jessica were both undergraduates who did work on the project as part of what at WPI is known as the major qualifying project. You can think of it as a senior thesis. My faculty collaborators in recent times have been mainly Brigitte Servatius, who I think some of you know, Randy Poppenroth, who is kind of a math, data science kind of person, computer science person. He actually has appointments in two departments and the data science program at WPI. And then Parag Okahan, who was at WPI for a number of years, but has recently gone back to his native Ireland. Okay, let's get started. Is it? I thought it was going to work. Let's see. Yep, there. So let me give you some basic background, because I'm going to assume that most, if not, and maybe all of you don't really know what a Kirchhoff graph is. Suppose you have a set of vectors, S1 through Sn. And the reason I use S as the letter is that when all this started, I'm thinking of these as vectors that represent reaction steps. Suppose you have n vectors in some vector space. The vector space should be over the rationals, or at least the vectors S1 through Sn should form only rational linear combinations. Suppose that exactly m less than n are linearly independent. We can actually deal with the case where they're all linearly independent, but that's actually not very exciting in terms of the Kirchhoff graph world. Then it's, of course, possible to write the vectors, the m plus first through nth vector in terms of the others, with some coefficients, which I've labeled as C tilde, and I've indexed kind of backward from the way you normally would, but there's a reason for that. But I assume this doesn't, that everybody understands all that. So then you can write the system of equations in matrix vector form, where S in this case is a column vector, where S1 through Sn are the entries of that column vector. And this is just standard matrix multiplication here, matrix times vector multiplication. That has to be 0. Well, what I've done is simply taken the right-hand side of the previous system, brought it over to the left, and formed this matrix. Of course, you can transpose the whole thing, and then you get something closer to what I want, which is S transpose, which is now a row vector with entries S1 through Sn. And then C over, I'll call it minus Qi. What I've done here is multiplied through by the least common multiple of all of those coefficients that we had in the previous slide. So the block C has only integer entries, and obviously Qi has only integer entries. This matrix C over minus Qi, I call N for null matrix or null space matrix. And notice that it has to be orthogonal to a row matrix R, row space matrix R, which can have the form QI on the left and then the C block on the right. And what this means is that the nth column of R is a basic representation for the step, the vector Si. Regardless of what vector space we started with, regardless of what the SI, the S vectors were, we might as well represent them by just the columns of this matrix. And that's what I'll be doing throughout. At some point, I may also use a matrix A or discuss other matrices that are row equivalent to R. So we'll construct Kirchhoff graphs for, I would say, the matrix R, or any matrix A that is row equivalent to R. If two matrices are row equivalent, they have to have the same Kirchhoff graphs. Okay, I think it's a good time to give an example. So here's a fairly simple, but certainly not the simplest example, but suppose R were this matrix, Q here is 3, and the C block is what you see right there. Then N has to be this matrix. And if we form, if we find a Kirchhoff graph, one Kirchhoff graph for this matrix R is what I'm showing here. The edges of this graph are the vectors, S1 through S4 in this case. You can think of the edges, the edge vectors as the edges of the graph, or you can think of it as being that we assign vectors to each of the edges. But if you think about assignments, and that's actually important for some of what we do, but the assignments can't be done just anyway. The assignments have to respect vector addition. The hash marks indicate that this is not that this is a multigraph. The same edge vector may lie several times on top of itself, connecting the same vertices. So I need 3 copies of S1 there and 3 copies of S2 here. And what's so special about this graph? What makes it Kirchhoff? Well, each of the vertex cuts, this one, for example, has to lie in the row space of the matrix R. So if you take the 2 rows of R and you add them together, what you should get, I think, is 3, 3, minus 1, minus 1. Notice that 3 copies of S1 go out of the vertex that I'm identifying here. 3 copies of S2 go out, and then 1 copy of S3 and S4 each go in. In what we do here, inward is the positive, inward is the negative direction, outward is the positive direction. You can do it either way. It's a little more consistent with the electrochemistry if I define it this way. So that's one of the conditions. Each of the vertex cuts has to lie in the row space of R. And I won't check all of them, but if you sat down and checked all of them, they are in that row space. Each of the cycles has to lie in the column space of N. So notice that if we do an S1 step here, then a minus S4 step, a minus S3 step, 2 minus S4 steps, and a minus S3 step, 2 step, sorry. What we have is this second column of N. did one S1. In total, we did two S2s, but in the negative direction, and we did three S4s in the negative direction, and we never did an S3. Every cycle, and for that matter, every walk or path through that vector, that graph, sorry, lies in the null space of the matrix N. And that's what makes it a Kirchhoff graph. Indeed, the cycles here span the null space of N. Okay, so let me talk about the application briefly. I'm guessing that nobody in the
I have a
audience...
brief question.
Yes,
Is there
sir.
a way to predict how many vertices are going to be in that graph in advance?
Not really. In fact, you can have, in the end, you can have as many as many vertices as you want. As we'll see, we can build bigger and bigger Kirchhoff graphs if we choose to. But even the smallest Kirchhoff graphs, in terms of the number of edges present, may have somewhat different numbers of vertices. Yeah. So I think the answer really should be no to that.
Thanks.
No problem. As I was saying, I assume nobody here is really into electrochemistry, so I won't say a lot about this, but I think it might be helpful to have some appreciation that this really does tie into an application. And in fact, my involvement on this came out of these sorts of applications. Suppose we have a reaction network, a simple one. A good choice is what's called the hydrogen evolution reaction network, maybe I would add, but HER network. It's made up of 3 steps, which for historic reasons, the first step is called the Toffel step, the second step is called the Volmar step, and the third step is called the Horowski step. Those are the names of 3 famous electrochemists, I think from the 19th century. And what these symbols mean is that you have 2 hydrogens. For the first one, for example, you have 2 hydrogens attached to reaction sites on the surface of a catalyst. And if this reaction proceeds in the forward direction, those hydrogen atoms come together to form a hydrogen molecule, H2, which goes off into the electrolyte, and you're left with 2 open sites. S is for site and not for sulfur in this case. This is a little cartoon, if you like, a little depiction of that. You start with the hydrogen attached to the catalyst, and hydrogen, I should say, hydrogen atoms are moving around, diffusing around the surface of the catalyst all the time, but every so often 2 of them get side by side, and then they pop together, combine, go off into the electrolyte, leaving 2 open sites. The reaction is reversible. It happens in the opposite direction too. So there's actually not exactly a preference for the forward reaction. Depending on the environment, the reverse reaction might be the dominant one. This is part of why batteries in computers are rechargeable. You can run the reactions forward and backward. Okay, I won't say too much, but this is that same kind of cartoon for the second step. A water molecule comes into a site. There are plenty of electrons down in the catalyst too. The water molecule donates a hydrogen to the site and pulls away a free electron, or an electron that it frees up, and that forms a hydroxide ion, which is what OH minus is. And the Horowski step is actually the most complicated in terms of what's going on. You start with water and hydrogen and an electron nearby, and like I said, there's always electrons nearby in the catalyst. this hydrogen and one of these come together to form a hydrogen molecule, but the water has to then pull away an electron to form hydroxide and leaves in the end a free site. So imagine these steps going on simultaneously, on and on, inside some reaction area. It turns out that if you have these three steps, a little linear algebra says that the overall reaction that comes out of this is what I call B here. And here I have to tell the electrochemist that the B is for AX equals B in linear algebra. That's why I chose B as the name. It is the outcome of that kind of linear algebra. It's an achievable overall reaction. What makes it an overall reaction is that it doesn't involve the sites, either free sites or those with hydrogens associated with it. It involves just the other species. As this reaction is going on, although the steps either free up or occupy sites on the catalyst, the overall number of free sites and occupied sites on the catalyst basically remains constant as the reaction's going on, because they're being freed up in one spot and opened up in others, and essentially that doesn't change. The overall reaction, therefore, can't involve those sites, and this is essentially the only reaction step that's possible, leaving out as a combination of the first three, only one that's possible, leaving out what are called intermediate species, the free sites and the occupied sites. Okay, I should go back a little for a second, sorry. Now we want to form vectors, the stoichiometric vectors. I should say, this is the stoichiometry for the reaction network. I don't know if that word means something to people, but this is the sort of bones of the reaction network. We want to form vectors where species that are on the reactant side of a step, they get positive coefficients. So the entry for S is 2, the entry for hydrogen molecules is 1 for this TOEFL step. And if it's on the product side, the entry for hydrogen attached to sites is -2. The entries on the reactant side are all given negatives. And any species that's not there in the first place is given a 0. And so that's the first. Actually, I should back up for a moment. This will be the second column, second vector that we're going to work with. Turns out that although we found it last, I want to put the overall reaction vector first. So the stoichiometry for the overall reaction will give us the vector I want to put first, then this one, then this one, then this one. We form a matrix whose columns are these vectors, and we row reduce that matrix. And if we want integer coefficients, we get this matrix R. So this is effectively the overall reaction vector, 2, 0, then the TOEFL step, then the Volmar step, then the Horolsky step, if I remember the order correctly. And a bit of linear algebra says this has to be the matrix N then. Not difficult. The Kirchhoff graph for this reaction network looks like this. And the point here, from the point of view of the electrochemistry, is that if you're trying to achieve this overall reaction going across this way, the way you achieve it in the reaction network is either an SH, a Horolsky step, followed by the negative of a TOEFL step, and then another Horolsky step, or you can do Volmar, TOEFL, Volmar, or you can do Horolsky and Volmar. And basically, not counting null cycles, which don't really contribute anything, and not counting the order that you do the steps, those are the three combinations that give you the overall reaction. That's really the null space part of this, and it corresponds to Kirchhoff's voltage law, that if you go around a cycle, you end up back where you started. And in this case, for example, if you go a Horowski step and a Volmer step, you get the overall reaction. So if you subtract the overall reaction, you have to get back to where you started. And this is with respect to all the species involved. The other thing, though, that's helpful is, and if anybody can recognize this, you obviously were paying really good attention back in electricity and magnetism class in basic physics. This is a kind of Wheatstone bridge, the way it's set up, the way the geometry has the vectors lined up. And what I mean by that is, if you think about it, the reaction rates, the condition that each vertex cut is in the row space means that the reaction rates for these steps all have to balance at each vertex. So in particular, the Horowski step plus twice the Toffel step has to equal the Volmar step. That is, the rate of the Horowski step plus twice the rate of the Toffel step has to equal twice the rate of the Volmar step. And what this means is that if you measure the Toffel rate, it will be 0 exactly when the Horowski and Volmar rates are the same. And whether or not the Toffel rate is positive or negative will tell you which of these two rates is larger or smaller than the other. And that is effectively what a Wheatstone bridge does in a classic basic physics experiment. So in any case, that's all I want to say about the electrochemistry, but this gives a graphical representation to electrochemists. They can look at this and think the way an electrical engineer would think about a circuit diagram. They can look at people who are chemical engineers or electrochemists can look at a Kirchhoff graph and get information about the reaction network. I should perhaps, I should add that all of the information about the rate balances and the cycles, it's actually all back in these steps. I haven't really done anything that isn't all in the electrochemistry, in the stoichiometry, but it's very hard, I think, to see the information in the steps. It's much easier to see it in the Kirchhoff graph. Okay, so let's talk about some of the mathematical issues then. One of the things that is true about Kirchhoff graphs is that most of the time they satisfy a uniformity condition. If the graph is Kirchhoff, if it satisfies that row space and column space, those conditions, then there also are the same number of S1s as S2s, as S3s, as S4s in the overall graph. In this case, every step is present 6 times. For S1, there are 3 here and 3 here. For S4, 1, 2, 2, 1. And the same is true for S2 and 3. When I first began drawing these things, I noticed that this was frequently the case, but not always. And I was very curious about why and exactly what the condition was that would give you uniformity. Turns out that a Kirchhoff graph must be uniform if the graph is vector 2 connected. And I'll define that term. A graph is vector 2 connected if and only if any pair of vector edges Si and Sj, before any pair of vector edges Si and Sj, there exists a cycle C such that the cycle vector is non-zero with respect to both Si and Sj. So the cycle vector chi of C should have to have non-zero entries for both Si and Sj. And to give you some sense of what that definition means, because I'm betting you haven't seen it before, let's look at a Kirchhoff graph that is not uniform. If you look at this, this is what we referred to as the tent graph, because it looks a little like a tent. It should be thought of as being in three-dimensional space, I suppose, projected onto the plane. S1 is twice in this graph. S2 and S3 are twice in, S2 and S4 are twice in this graph, and S3 is in the graph 3 times. And so this is an example where it is not uniformed. If you look at R here, the thing is that that column, third column, has a 1 in the third row, but everything else is 0. And what this means is that in some sense, you lose control of what's happening with this third S vector. You can put it anywhere you want on the graph. It also means there's no flow in that direction. So the rate balances just ignore it. But why isn't this vector 2 connected? Well, if you think about it, if I do S1, S3, S2, S4, minus S3, actually it was minus S3 here, and S3 coming back. If I go around, say, this cycle, notice that that's a cycle that contains S1 and S3, but it turns out to be have an entry in the chi vector of 0 because we transversed S3 twice in opposite directions, so they cancel out. And there's no way of including an S1 and an S3 without canceling out the S3. And that makes this graph not vector 2 connected. And so the uniformity requirement goes away. To prove this, and I won't go through all the details of the proof, but let me quickly say that the way to prove it is you have to split up the vector edges from the overall edge count. So every edge, every time a vector occurs, even so S1, for example, we give it a separate edge number. So in this case, edge 1 and edge 2 both are vector S1. Same is true for the rest of them. The last two SNs are E capital N minus 1 and E capital N. If we then form the digraph incidence matrix, so this is the incidence matrix for the E edges and the vertices, then the vector graph incidence matrix is a product of those two. You simply product them together to cancel out the E's, and this tells us which vertices each edge vector is assigned to. And notice, unlike the standard incidence matrix, the same edge may have connect up different vertices. Here, it would appear that the edge S1 goes from the first vertex out of the first vertex and into the second vertex twice, and then it also goes out of the M minus first vertex and into the fourth vertex once. Okay, a bit of linear algebra and basically arguing elements are on both sides gives us that the transpose of this T matrix multiplied by the null space of Q is the same as the null space of QT. It's just a little bit of linear algebra argument. We then define a matrix T transpose T. If you think about it, this will have to be a diagonal matrix, and the number of edges of S1 assigned to edge 1, SI, is the ith element on the diagonal of H, And uniformity would be if all those diagonal entries are the same, say eta. That's what we want to show in the end. We then need a little lemma, which is based on that previous equality. And what we want to say is that if there is an entry in the null space of Qt, then H times that entry also has to be in the null space of Qt. It's not a hard argument to do. But then you want to start thinking about what happens when the null space of Qt has a basis of vectors in it. And to start with, we start with the span of one vector. Suppose it's the span of a single vector. Then it turns out that if the entry in B, the ith entry, is non-zero, it will be the case that HII has to be the same independent of I. And this is also what goes wrong when you have when you lose control, what I said earlier about losing control on an edge. You end up with a 0 in this position. And if you end up with a 0 for each of the for every element of a basis of the null space of Qt, then you don't get any, you can't make the argument work. As long as you have vectors in the basis of the null space of Qt that basically touch or involve all of the edge vectors, then you can get an argument, we can get an argument that says that they all have to be the same multiplicity. And that's the uniformity argument. And I should particularly give credit for Tyler Reese for working through all of the details and you know, getting all of this lined up correctly, and realizing that this definition of vector 2 connected was the key thing to make it work. Okay, so I want to say now that we can use this argument to this uniformity to construct Kirchhoff graphs. So here's a simple case. Suppose we have this row matrix and we consider multiplicity 2. So we're only looking for graphs with 2 copies of each edge vector. So we start with a vertex somewhere and we put in a set of vectors, edges, that is one of the entries in the row space of that matrix R. And this is one possible, we think of this as a southwest corner of the graph. And this is one of the possible edges, edge arrays that might come out of that southwest corner. And then we move over, say, to this vertex, and we start putting vectors out of that vertex, again, consistent with this new second vertex being in the row space. But now we notice that if we tried to use the same combination that we used in the first case, we have a problem because we're considering only graphs, looking for graphs of multiplicity up to 2. We now have, if you can see that little number, that's a 2. And that means we have 3 copies of S1. That's 1 too many. So this vertex cannot have the same set of vectors that the first vertex has. So we try a different one. We try this arrangement, which is another possibility that's consistent with being in the row space. And this does not violate any rules. We've used up both copies of S2 now, but that's okay. Maybe that's the right one. We move on to another vertex and we try this. That's a no. Too many copies of S2. That's still a no. That's a no. That's a possibility. Hasn't violated anything. Come down to here. You can see where this is going, perhaps. That's a no. That's a no. That's a yes. That's a Kirchhoff graph. And this little process, obviously doing it by hand would be laborious, but the point is that you can have a computer do this now. This is basically a greedy algorithm that goes through and tries all the possible combinations and just stops when it finds something. For m equal 2, in this case, you can find that there are exactly these two Kirchhoff graphs and that there are no others. And so these are the two smallest Kirchhoff graphs for this matrix R, or any matrix, any stoichiometric matrix, I could say, that's row equivalent to R. And this was the one for the HER reaction network that we started with. Okay. We can also tile Kirchhoff graphs together if they have the same vectors in them. Notice that what I've done here, I have a graph where the edge multiplicity is 4, and it's basically take that first square graph we had a moment ago and put the diamond on the, if you like, right side of it, and then add in all the edges that were there. You have as many edges here now as in both of those graphs combined to start with. And this will also be Kirchhoff. It has to satisfy exactly the same edge cut, vertex cut conditions. It has to satisfy the same cycle conditions. So this is also Kirchhoff. And this is what I would call a composite Kirchhoff graph. I could pull them back apart. I can put them together. I can do this. I can take the square and add one there. I can add another square there. This is still composite. This is also composite. But notice that we weren't just throwing the squares together randomly. We've actually formed that other diamond graph in the middle of that set of squares. And so what I can now do is remove the diamond from the middle and get this Kirchhoff graph, which has should be 3 times, I guess, the number of vertices as the of edges of edge multiplicity as the first one. But it's different from the previous ones. This Kirchhoff graph is still prime, what I would call prime. And what I mean by that is if you pulled an edge out of this, then you'd have to keep pulling edges out to try to put the associated vertices back into the row space. And you'd end up pulling all the edges out. The only way you'd get back to the row space is if you removed every last edge and went to nothing, the null vector being in the row space. That's different from this composite, where obviously we pulled out a bunch of edges, the diamond Kirchhoff graph from the middle here. And sorry, didn't lose Kirchhoffness. This is also a prime Kirchhoff graph, but has multiplicity bigger than the first. And we can keep this process going. This is Kirchhoff also, still bigger. And obviously we could continue this process as long as we wanted. This means that this family of Kirchhoff graphs has as many primes, has countably infinitely many prime elements. And you could do them in other ways too. There's no reason they have to be just this sort of arrangement. Anytime you do the tiling, you can form the sort of opposite graph, tiling with one of them and removing the other one. this is a proof for this particular set of edge vectors, but the process actually applies to any Kirchhoff graphs, at least if you have two distinct prime and I would say fundamental Kirchhoff graphs to start with. Okay, let's go to another example, and I'll say a little bit more about fundamental sets, and we can finish up with this. Here's another row matrix. It's almost like the one we started with, but I've gotten rid of minus signs. I've done examples with lots of matrices, and it just happened that this was what I had handy. But for this row matrix and the associated null matrix, it turns out that if you check out the run the computer code and carefully do the algorithm, or even if you did it by hand, although it would take a while, you would find that you had no Kirchhoff graphs until you got to edge multiplicity 6. And the first Kirchhoff graph with edge multiplicity 6 might be this one, but the computer also would find this one, and this one. They all have the same number of edge vectors. They have different numbers of vertices, at least these are different. And I don't remember the count. Is it 8 for each of these? And this is 7, and this is 9, I think, 10, I forget. Anyway, notice though that something else is true. So there are 4 Kirchhoff graphs here, but only 3 are fundamental, and you can choose any 3 you want as the fundamental set. And the reason is, it's this tiling thing again. If I take this Kirchhoff graph, actually, let's start with this one. If I take this Kirchhoff graph and pull it down and put it here so that this central vertex here is identified with this central vertex, that first graph would lie right in the middle here. And what we would then have is the same composite graph as you get if you take this graph and you pull it down and you line up these 3 vertices with these 3. So if you did what? I'll call this F2 plus F3 minus F1, you'd end up with F4. So F4 is not needed in a fundamental set. You can get all 4 of these by tiling these 3. You could choose any 3 though. Okay, notice that something else is true. Let me go back. These 2, the first one and the fourth one, are symmetric. If I took this projection on the plane, in fact, the graph really is embedded naturally in the plane. If I rotated by 180 degrees, and then if I reverse all the vectors, I would end up with the same graph that we started with. If you can imagine in your mind spinning it 180 degrees about that central vertex, you'd have the same shaped graph, but all the vectors would be backwards. But then when you flipped all the vectors one by one, you'd go back to where you started. Same thing is true down here. These 2 are symmetric. These 2 are not symmetric, obviously, but they are, I would say, chirals of each other. They're kind of mirror images. If you rotate each of these by 180 degrees and flip all the vectors, you get the other one. And that's what makes them these 2 chirals of each other. Chirals is a word from the chemistry world that I think is useful here to describe these graphs. So that's what I just said. And a proposition, not a hard proposition, is that anytime you rotate a Kirchhoff graph embedded in the plane by 180 degrees and reverse all the vectors, the new graph also has to be Kirchhoff. It has to satisfy all of those Kirchhoff conditions. Okay, what's the structure of these families? Well, there's going to be what I'll call M star, which is the smallest multiplicity for which there's a graph. If you try to find a Kirchhoff graph with multiplicity less than m star, you'll find no non-trivial Kirchhoff graphs. We could discuss whether or not the null graph, which is one vertex, no edges, is or is not, should or should not be made Kirchhoff, but it's not a very exciting Kirchhoff graph. So there'll be this first multiplicity where there, or lowest multiplicity where there is a Kirchhoff graph. At m equals n star, there will be a set of prime Kirchhoff graphs, and then a subset, possibly equal to the full set, possibly smaller, will be fundamental. And you can use it to generate an entire family of Kirchhoff graphs. The next Kirchhoff graphs in that family will occur when you get to 2m star. There'll be no graphs with multiplicity between m star and 2m star, and then you get more Kirchhoff graphs at 2m star. They won't be fundamental, but some of them will be prime, some of them will be composite. And let's see. Suppose we take this matrix. I'm changing matrices again. This is another row matrix. Computer can find the graphs for this one. It turns out that computer will tell you that m star, the lowest multiplicity for which there are any Kirchhoff graphs, is 12. And then the computer will find 131 Kirchhoff graphs for this matrix, all of which have 12 copies of each of the four vectors, S1 through S4. The only one I'll draw is this one. This is the smallest. And if you were interested in this in terms of the electrochemistry, this is almost surely the Kirchhoff graph you want. The other ones are bigger and much less compact, and I don't think are generally that helpful. I think this would be the most helpful if the reaction network that you were interested in led to this matrix. But in any case, you can see this is way beyond what somebody can do by hand. These graphs are actually very hard to draw by hand, and the computer codes that Jessica and Marcel developed have greatly improved our ability to come up with examples and see what's really going on here. In terms of open questions, I guess I'm getting close to where I should be stopping. If you have a matrix R to start with, so you have the vectors and you've formed your matrix R, what's going to be the value of m star? Is there any way of finding it other than that algorithm where the computer searches for it? Is there something you could look at in terms of R or the columns of R and say what m star is going to be? I don't know the answer to that at this point. For this m star, how many Kirchhoff graphs are there going to be? How many prime Kirchhoff graphs? It varies, I know, but I have no way of predicting it. I would not have been able to start off and guess, if I can go back to that matrix, that this would have only 4 when m is equal to 6, and that this would have 131 when m is equal to 12. I couldn't predict that at all. And then the last one that I think is particularly interesting is, are there larger Kirchhoff graphs that are not generated by the small fundamental set? So for example, could there be a Kirchhoff graph with 73 copies of each edge? Some large prime number completely unrelated to the ones that the small ones that we start with and that we build up from. I think the answer is probably no, but I certainly don't know for sure. Okay, that finishes my talk. I'm happy to have questions, and I do thank you for your time.
Let's thank the speaker. And questions. I will stop the recording now.